back to the next lecture in module 4 on solution of discrete algebraic systems. We had a look at features of discrete algebraic systems which are encountered in CFD in the last lecture, and we also had a look at methods for nonlinear systems. In this lecture we are going to focus on direct and basic iterative methods for linear systems and accelerated iterative methods for linear systems if time permits today. So, let us have a recap of what we did in the previous lecture. We discussed what are the basic features of the discrete algebraic systems encountered in CFD applications are, and then we discussed the two basic methods for nonlinear systems, that is a sequential iteration procedure and Newton-Raphson method. In this lecture we will focus on linear systems. We will first have a brief look at few direct methods and then few basic iterative methods for linear systems. So, we will start off with the direct solver for discrete linear algebraic systems. In particular, we will derive the tri-diagonal matrix algorithm. So, this is one of the very few direct solvers which are extensively used in CFD. And then we will start off with iterative methods for linear systems. We will have a look at few basic iterative methods. Now, let us have a look at basic features of the numerical methods for linear systems. We have direct solvers. What do we mean by direct solvers? The ones which work directly on our given system of equations, and if we had infinite precision in calculations, they would lead us to an exact solution of the problem without any approximation or any numerical errors. Typical examples are Gaussian elimination procedure and factorization based procedures like LU decomposition. There are many more, and we have got literature full of different decomposition procedures for solution of different types of linear systems. Then we have also got iterative solvers. Typical examples are our Gauss-Seidel process, SOR, which is successive over relaxation scheme, pre-conjugate gradient method, multigrid method, and host of many iterative schemes. We have got books full of these iterative methods as well as direct solvers available. So, in this lecture we are going to have a look at few simple representatives which are extensively used in CFD. Now, which particular solver we would use in our numerical code, that will depend on the nature of the system matrix. For example, if our system is symmetric and positive definite, this would be the case if we had used center difference approximation for a Poisson problem, and similarly if you use a Galerkin finite element process for any Poisson equation. Both of these discretization processes will lead us to a symmetric and positive definite system, and in this case we have got simplified versions of decomposition process. For instance, the Cholesky decomposition, which works more efficiently compared to LU decomposition, and similarly we have got specialized versions of iterative solvers such as symmetric SOR and preconditioned conjugate gradient method. But if you are not sure if your system is symmetric and positive definite, that is to say our system is what we would say a general system, and we know for sure that it is going to be invertible, the solution exists for, then we can use direct solvers such as LU decomposition, Gaussian elimination, and so on. And iterative solvers, some of them are Gauss-Seidel, successive over relaxation scheme, GMRS, and biconjugate gradient method. Now, these methods for general system, they take definitely take more computation time compared to the methods which would for symmetric systems would take. Let us introduce a term which we would use very often in presentation of algorithms. This is called computational complexity. So, it is essentially linked to the number of arithmetic operations. So, number of arithmetic operations involved in a numerical solution of an algebraic system is referred to as the computational complexity. So, this term is also extended for any algorithm, whether it is being used for an algebraic system or otherwise, and it depends on, in our context, the order of system, that is the number of unknowns capital N, It also depends on the nature and structure of the system matrix. By nature we mean whether it is symmetric, positive, definite, or it is an unsymmetric system. By structure we mean whether it is a sparse system with multi-diagonal structure, a banded matrix, or it is a full matrix. So the computational complexity will depend on all these features. It will also depend on the choice of the solution algorithms. The different algorithms have got different computational complexities. In general, computational complexity of direct solvers, for example, a Gaussian elimination or LU decomposition, it grows as order n cube, and this one exception to it, the specialized solvers such as TDMA and similarly cyclic decomposition, which are applicable to very special matrices, they are exceptions to this rule. So when we talk about the computational complexity of direct solvers of being of the order O n cube, we are talking about our general system, not a specialized solvers such as TDMA. And we have got another category of algorithms which we call fast methods, more precisely as fast iterative methods. Thus their aim is to obtain a computational complexity which grows with the as system size, that is computational complexity is offered of the order O n or order O n log n. Now this is the ideal case or ideal aim which an algorithm developer aims at. Most practical algorithms will have much higher computational complexity than O n or O n log n. But there are few beautiful iterative algorithms available specifically on a structured grid or geometric multigrid. It can lead us to O n complexity. Now given the computational complexity of these direct solvers being O n cube, these are normally preferred for smaller systems, whereas if you got a large system which we typically encounter in CFD analysis. Just remember, if you want to have a numerical simulation of a typical industrial flow problem, even with Reynolds average Navier-Stokes simulation, the number of grid points would be in many thousands, maybe close to 1,000,000. So our order of the system, algebraic system in such a case would be of order of millions. Similarly, if you want to perform a large area simulation or direct numerical simulation, the order of the system would be in billions. So in such cases we cannot afford to use a direct solver, we would use iterative solvers for such large scale problems. Now let us have a look at our specific case of FDM, FEM or FEM discretization. When we apply any of these discretization schemes to our governing equations, what we get is a sparse system, and as I just mentioned few moments ago, order of the system is usually large in millions and billions. Hence direct solvers such as Gauss elimination or LU decomposition are rarely used. In fact, they are not at all suitable for these systems due to their computational complexity, which is of order O n cube, and storage requirement which are of order O n square. Even our system matrix might take only storage of O n. In the elimination process or in decomposition process, we get the intermediate matrices which might require a much larger amount of storage. So hence these methods, they are not used per se as solvers for large scale CFD applications. We will see one specialized version of Gaussian elimination for one dimensional problems, which leads us to our TDMA, and similarly this LU decomposition, some specialized versions, what we call incomplete LU decompositions, they are used as preconditioners for iterative solvers. So that's in practice, that's the only use such of direct solvers in CFD. So special variants for direct methods for a specialized situation, we have got like our tri-diagonal matrix algorithm, which we say TDMA in short, for one dimensional problems, because in one dimensions we have used a central difference approximation with a 3-point computational stencil, we get a tri-diagonal matrix. And this TDMA, we will see a little later that it has got a computational complexity of O n, We can also derive for multidimensional problem some iterative schemes, what we call alternative direction based schemes, which are based on TDMA for multidimensional problems. We will not take up these schemes in the present lecture. If you are interested, you can have a look at this algorithm in the book of Fersiger and Perek, or in the book by Chung, or in fact you pick up any CFD book, it will give you some application of this ADI which is based on TDMA. And similarly, a specialized version of LU decomposition for band diagonal systems are also available for band diagonal systems which are obtained on unstructured grid when we apply finite volume or finite element discretization. For details, please have a look at the numerical ResPech book by Press et al. Now let us come to the tri-diagonal matrix algorithm, which is applicable for a special case of one-dimensional problems. Now let us derive this algorithm ab initio. And this particular algorithm is just a special case of Gaussian elimination. In fact, it is just the Gaussian elimination applied to our current situation. So it is essentially Gauss elimination procedure applied to tri-diagonal systems. So our generic equation, let us see how do we write our generic equation on a 3-point computational stencil. P E W, P stands for I, E stands for I plus 1 and W stands for I minus 1. In shortened form we write this equation as A W I for a generic scalar quantity phi I minus 1 plus A P I phi of I plus A W, sorry, A E I, A W we have already taken care of. So, A E I phi of I plus 1 is equal to B I, where I varies, let us say, from 1 to n. So, this is our equation. If you look at the matrix per se, now let us put it in matrix form. AP1, AE1, we will get only these two entries in the first row. Phi 1, phi 2 and so on. Let us reach at phi I and phi n. On the right hand side we have got this B I, B 1, B 2 so on, B I up to B n. Let us complete our tri-diagonal structure, the matrix. So, in the second row we will have AW2, AP2 and AE2 and so on. So, that is how we will proceed. In the ith row we will have AWI, API, AEI last one we have got our A Pn, and to the west we have got AW of n. Now, in Gaussian elimination, what we want to do, we would like to eliminate all the entries in the lower half of the matrix. So, we would like to eliminate, now here we have got only this lower diagonal to be eliminated, and for that what do we do? For instance, we want to eliminate this AW2 entry from the second row. So, for that, or as a process for Gaussian elimination, for second row, we do not have to do anything for the first row, because those this entries, they form the part of the upper triangular matrix. So, that we will leave as such. Now, if we want to eliminate AW2, what do? We have to multiply the first row R1 by AW2 by AP1 and subtract it from R2. R2 is our row 2. Now, you can clearly say that which entries would be affected of the row 2 when we perform the subtraction process. AW2 would be eliminated, that will become 0. AP2 would be affected, that is all. The AE2 will not be affected, because the corresponding entry, the entry in the same column in the first row was 0. So, what we get as modified entries would be that AW2 becomes 0 and our AP2, this is now assigned a value for the existing value of AP2 minus AW2 into AE1 divided by AP1. Our right hand side will also get modified in the same way, because we are performing the same row operation on the load vector as well. So, this B2 would be modified as B2 minus AW2 by AP1 into B1. So, we can clearly see that the same process can be applied to any of the subsequent rows. For instance, for eliminating the AWI entry from the ith row, we will multiply the I minus 1th row by AWI divided by API minus 1. So, AWI gets eliminated. So, thus in general, thus for I is equal to 2 to n, what we need to do, our forward elimination process becomes API this becomes API minus AWI into AE of I minus 1 divided by AP of I minus 1 . BI, this becomes BI minus AWI into BI divided by API minus 1. So, this is our forward elimination process which we need to apply for all the rows starting from second row up to the last row. So, once we have completed this forward elimination, how do we obtain the solution? In the last row we are left with only one entry, that APN phi n is equal to Bn. So now our solution is obtained, solution by back substitution. We would proceed in backward order, like first we will obtain phi n. So phi n is now given by Bn divided by Apn. And how about the remaining entries? Let us say in the ith row we are left with only entries API and AEI. So our ith equation is now with modified coefficients, that is API phi I plus AEI phi f I plus 1 is equal to Bi. So this leads to equation for phi I is equal to Bi minus AEI into phi of I plus 1 divided by API. Now we need to apply this formula for I is equal to n minus 1 to 1 in this order. Okay, so this is just a very standard Gaussian elimination process applicable to a specialized case, and the number of operations which we performed, they are proportional to the number of unknowns in our system. So if you want to program this method, the pseudocode for this TDMA algorithm becomes very simple, and I would encourage you to write a subroutine or a function based on TDMA. So this I would give as an exercise. Write a function or subroutine based on TDMA for solution of tridiagonal system arising in let us say finite difference analysis of one dimensional problems. For your benefit, if you want, you can just write the pseudocode. In forward elimination, we just need to apply the elimination part of the formula. So we can say for I is equal to 2 to n, do what? Modify AP. So API that gets modified as API minus AWI into AEI minus 1 divided by API minus 1, and your BI gets modified as BI minus AWI into BI divided by API minus 1. And then our back substitution phase. Phi I is equal to Bn divided by Apn, and then for I is equal to n minus 1 to n, do phi I is Bi minus Aei into phi of I plus 1, this whole thing divided by API. So that's all. So you can see this is very simple to code. In fact, the total number of code lines would be 4 plus 4, 8. So in a total of 8 code lines, you can write this algorithm in a Fortran or C language. And there are some things which are commonly being multiplied. You can take them out and maybe introduce 8 additional line of code, but reduce the number of multiplications and divisions by doing that. For instance, this AWI divided by API minus 1, which we had in forward elimination, for each I, it can be calculated only once. This division process can be done only once, and this local variable can be multiplied with respective entries. So forward elimination, whereby we modify this API, the diagonal coefficients, and as a consequence our right hand side also gets modified. Once we have completed this, we can easily get our solution by the back substitution process. Now let us move on to the iterative solvers, and there are primarily simple classification of these iterative solvers. They are put in two categories: basic iterative solvers and accelerated iterative solvers or advanced iterative solvers. So basic iterative methods are typical examples are Jacobi's method, Gauss-Seidel method, and SOR. These methods are very easy to program. We will see their algorithms in a short while from now. So they are very easy to program. They require very little computation time per iteration, but they have very slow convergence. So for very large systems which we have in CFD, for instance, we want to solve the pressure Poisson equation involved in large eddy simulation or DNS of turbulent flows, where order of system is of close to a billion, a few billions. This Gauss-Seidel, Jacobi, and SOR would require many millions of iterations. And because of slow convergence, with the exception of SOR, Gauss-Seidel and Jacobi, these two methods or their variants, they are not used as stand-alone solvers. By stand-alone solver we mean that they are used as a equation solver. So only SOR with an optimum value of what we call over relaxation parameter, it is used in CFD codes. Jacobi and Gauss-Seidel we do not use as stand-alone solver. All these basic iterative methods, they are primarily used as what we call smoothing or relaxation procedures in multigrid techniques. We will take up this multigrid techniques in the next lecture. So both say this category of iterative methods, they are primarily used as smoothing or relaxation techniques. And there is one more usage which we have got, these methods can also be used as preconditioners with Krylov subspace methods. We will have a look at one or two methods of Krylov subspace family, namely conjugate gradient method for symmetric systems and biconjugate gradient method for general systems. And Jacobi's method is used very often as a preconditioner to these Krylov subspace methods. One more feature, attractive feature of these basic iterative methods are that they are very easy to parallelize. That is to say, if you want to use a massively parallel computer with multiple cores, wherein we would like to solve one subset of problem on different cores, these Jacobi, Gauss-Seidel or SOR methods can be easily written for such machines. In fact, their version would not be very different from the version written for a serial machine. So, thus it and the advantage which these basic iterative methods possess. Their only downside is their convergence rate is very slow. Next is our accelerated iterative methods. Why we call them as accelerated? We will get to know when we take up each of these methods. For instance, say this conjugate gradient method. In this conjugate gradient method and GMRS method, the corrections are chosen in specific directions to accelerate the convergence of iterations. So, that is why we refer to these methods as accelerated iterative methods. Similarly, multigrid techniques, they employ the solutions at multiple grid levels. We will have a sequence of nested grids, and the corrections are computed at different grid levels, which will enhance the convergence of the iteration process. Now, the multigrid methods can be used as standalone methods on structural grid. We have got two formats of multigrid techniques. One is what we call geometric multigrid, wherein we use a sequence of nested grids. So, if that were possible, if it were possible for us to generate a sequence of hierarchical grid structures, then we can go for what we call geometric multigrid. On simple rectangular geometries, we can easily generate a hierarchy of nested grids in the context of structured grid techniques. It's more difficult if you have got unstructured grids. For instance, if we want to use finite volume or finite element method on unstructured grid, we can still devise multigrid techniques on that, but some of the operators which are required for multigrid techniques, their derivation becomes a bit more tedious task. In such situations, recently a new set of techniques have been proposed which are called algebraic multigrid techniques. Now, these algebraic multigrid techniques, they do not require us to supply a sequence of hierarchical grids. All that we need to supply is our matrix, and it creates so called coarsening and prolongation operators just based on the structure of the matrix itself. So, such techniques, that is why everything is being done algebraically. So, these are called algebraic multigrid techniques. And today most of the commercial CFD packages employ some form of multigrid method or Krylov subspace method. In fact, most of them, what they would do, they use this multigrid method as a preconditioner for Krylov subspace method. Now, let us come back to our basic iterative solvers, because we might or we would use some of them as preconditioners for Krylov subspace methods or multigrid methods. So, let us see few basic iterative methods, like the first one is our Jacobi's method, the second one is Gauss-Seidel method, and third one is successive over relaxation method. So, let us have a look at the algorithm for these methods. The first one is Jacobi's method. So, a system, let us write it as A x is equal to b. So, if you want to write it in index notation, we can also write it as the ith row of this system, or rather let us call it ith equation, that will write as sigma a I j x j is equal to b I. Now, let us separate the x I term. So, we can rewrite the left hand summation as sigma I is equal to sigma j is equal to 1 to I minus 1 a I j x j plus a I x I plus sigma j is equal to I plus 1 to n a I j x j is equal to b I. Let us transfer the terms which do not involve x I on the right hand side. So, you get a I x I is equal to b I minus sigma. These two summations we can combine and we can write them in a shorthand form. J is equal to 1 to n with the condition j not equal to I. A I j x j or x I is equal to 1 by a I b I minus sigma j is equal to 1 j not equal to I to n a I j x j. Now, this basic relationship can be utilized as an iterative scheme, and this is what Jacobi proposed, that look, if we had the guessed value, or if we start off with some guessed value of the vector x, based on those guesstimates we can obtain an improved estimate for the different components of the vector. So, this iterative scheme becomes guess x0. Now, let us put our iteration counter as a subscript. So, let us guess an initial value which we will denote by subscript of 0, and then we will obtain the next iterate x I k plus 1. This can be computed in using the values at the previous iteration, 1 by a I b I minus sigma j is equal to 1 j not equal to I to n a I j x j k. So, this is a simple algorithm. We cannot think of anything simpler, and if you compare with what we discussed for nonlinear systems, it is very similar to a Picard iteration, or vice versa. Maybe Picard iteration might have been obtained drawing an inspiration from Jacobi's method. Okay. And as we have noted, this scheme is very simple. At one moment we need only the entries corresponding to the ith row, that is the coefficients aii, aij for all j's, and we need the corresponding components. So this is why computations in each iteration are very fast. So here we can say that k is equal to 1, 2 and so on till convergence. The downside we have already noted, convergence is very slow. Is there something which we can do to improve the convergence of this Jacobi iteration? One of the simplest possible things would be, specifically in computer implementation, the moment we have generated a new estimate xi k plus 1, we do not put the values at k plus 1th iteration in a separate vector. In fact, old values are overwritten. Okay. So should we not use the already available new values? And if we can use the new values, hopefully the convergence can be improved. So that was the basic premise of the Gauss-Seidel method. Our basic equation remains the same, the starting point, that is we started off with a simple equation. The ith equation was j is equal to 1 to n aij xj is equal to bi, and this, using this we got a modified form for xi, or xi can be written in terms of the remaining components of the vector. So 1 by aii bi minus sigma j is equal to 1 j not equal to I to n aij xj. So when we used the values at the previous iteration, that is sometimes also referred to in Jacobi iteration, that we are trying to annihilate the residual involved in ith equation by using the values at the previous iteration level. What was suggested by Gauss and Seidel was that, look, use the values which have already been computed at a given xi count. So we will start from I is equal to 1, 2 and so on. So this equation holds good for all I values. So our iteration process what do we do is, starting from initial guess x of 0, for k is equal to 1, 2 and so on, iterate till convergence. And what is our iteration process? We said that xi at k plus 1 is equal to 1 over aii within bracket bi minus. Now let us break this summation term into two parts, one which would use the values already obtained at this iteration level, that is sigma j is equal to 1 to I minus 1. For these indices j is equal to 1 to I minus 1, we would have obtained a new iterate. So use that value, that is aij xj k plus 1, and then the next part minus sigma j is equal to I plus 1 to n aij xj k. So this simple modification to Jacobi's algorithm leads to a rate of convergence which is slightly faster than Jacobi's method, and this is what is our celebrated Gauss-Seidel method. There are versions of Gauss-Seidel method which are specifically designed for parallel computers. Some of them have what we call red black ordering of the nodes, or rather the planes, in multiple dimensions. So if you are interested, you can have a look at these versions in some of the standard books which we will mention at the end of this lecture. The next method, or the last method which we are going to have a look at in this series, is what we call successive over relaxation. It is popularly known by its acronym SOR. And what is the fun about this successive over relaxation technique? It says, look, whatever value or iterate or the new solution which we have obtained, this xik plus 1 by Gauss-Seidel iteration, do not take that as a final value. In fact, the final value at a given iteration level should be a weighted average of the value which we obtain from Gauss-Seidel and the value at the previous iteration. This simple modification works wonders in the convergence of this scheme. So if I write this as xik plus 1 in our Gauss-Seidel algorithm, let us put it under subscript to it. So in terms of this, our successive over relaxation method say that, look, now xik plus 1 is omega times xi of k plus 1 Gauss-Seidel plus 1 minus omega times x of k, where omega is a scalar quantity between 1 and 2. So omega is always taken greater than 1, so that is why it is called as over relaxation factor. The previous shortened form I wrote just to establish the closed link between the SOR and Gauss-Seidel. For programming purposes, we can now write the expanded form. That xi k plus 1 SOR is equal to omega times or omega divided by aii within brackets bi minus sigma j is equal to 1 to I minus 1 aij xj k plus 1 minus sigma j is equal to I plus 1 to n aij xj k plus 1 minus omega times x k I. So, there is a subtle difference here. Even this x I k plus 1 g s prime, I would like to write that as, because here and this formula, this x j k plus 1 on the right hand side, they are the ones which are the current iterates obtained by our SOR algorithm. Now, on a structured grid, on uniform structured grids, optimum estimates of omega is available. In fact, there are formulas, there are theoretical formulas which you can find in any book which gives SOR method, theoretical formula to compute omega optimum in this case. But on general grids, if we do not have wherein we cannot find out an estimate of omega opt, a rule of thumb value for omega is, you take some value close to 1.7 or 1.8. This would give us a reasonable rate of convergence. We saw something similar waiting in our case of nonlinear problems. In nonlinear problems, we take omega to be less than 1. So, that process is referred to as under relaxation. But in the case of linear systems, we always use over relaxation, that is, a weighting omega would be chosen to be greater than 1. Okay, so that brings us now to the close of our lecture on the direct solvers and basic iterative solvers. For further details, you can have a look at these two books, that Press et al.'s book on numerical recipes. This gives the methodologies, methods, algorithms, as well as codes for direct solvers and iterative solvers. For detailed description of iterative methods for sparse linear systems, this is what we encounter in CFD. This yet another nice book by Saad, published by Siam in 2003. This is a definitive reference for basic as well as advanced iterative methods with specific applications to the sparse systems obtained from finite difference, finite volume, or finite element discretization of partial differential equations. So, for details you can have a look at this book. This PDF is easily available on the net. And then this nice collection of routines on the web. There are many resources, but there is one very reliable resource which is called netlib, http://www.netlib.org. So, you can find many routines related to the solution of linear systems on this site as well, which can inspire you or help you develop a better understanding of these methods as well as to develop your own computer codes. So, we stop here in this lecture, and the next lecture we will take up accelerated iterative methods for sparse linear systems.